Okay, so the next part of simple harmonic motion that I want to talk about is how position, velocity, and time are all related. And to do that, we're going to use what's called the circle analogy. So before I get too much into what's drawn inside the circle, I want you to think about, okay, an object that is traveling in a circular path. Okay, if it was a tennis ball on the end of a string, you just go around and around and around in this circle. Okay, just goes up, round, round, round. Okay, but let's say we weren't looking at it from up above, looking down on it. What if we were looking from the edge? Okay, it wouldn't necessarily look like it was moving in a circle. What it would look like is it would look like it was traveling to this side, and then back this way, and then this way, and then back this way again, and then back to the other side. It would simply look as if it was oscillating back and forth. Okay, just like a simple harmonic oscillator. And then this distance, the maximum distance it gets away from this middle point, okay, would be represented by the amplitude of the object. Okay, its maximum displacement this way and its maximum displacement this way, all from this zero position. Okay, so if I go back and I take a look at my circle again, knowing that this side of the circle compared to this diagram is positive A, and this side of the circle is negative A, but the radius is always A, okay, or the amplitude is always A. If the object is over here, then its position, where it will look like it is positioned, would be equal to the cosine, because this is the adjacent side here, the cosine of this angle times A would give us the position. Okay, so over here you see that I've made this little equation here that says x, the position, is equal to the amplitude times the cosine of the angle. Okay, something that we're going to introduce right now is something called omega, which is the angular frequency or also the angular speed. And this might ring a bell from math class possibly, but we measure omega in radians per second. If you don't know what a radian is when the arc length is equal to the radius, that particular angle, that is equal to a radian. Okay, 2 pi radians make up an entire circle. Okay, so it's almost like you're measuring an angle when you measure something in radians per second. If you take radians per second and you multiply by a time, then you're going to get some sort of angle out of it. So if you look at this, I've told you that the angle could also be thought of as omega, which is again in radians per second, times time. So we get x equals a cosine, and instead of using theta now, we'll use omega times t. Something that is a nice little fill-in, though, that you might be a little more comfortable with is omega can also be written as 2 pi times the frequency, or, because frequency and period are inverses of each other, 2 pi over t, over the period. Okay, so there are some various equations that come out of this, and I know they're going to get a bit overwhelming. For those in IB, your copy packet or your equation packet has all of these. For AP, they basically have none. So AP is going to have to work a little tougher here or a little harder to get some of these equations straight. So a couple things that we want to say here. Okay, if the position is at A, so meaning that it's all the way out here, from the side view, okay, by the time it reaches this outside point, it's going to appear that the velocity is 0 at that spot. When it's on its way this way, here is where it's going to seem like it's moving really fast. And then it slows down to here, comes to a rest, then speeds up, maximum velocity here, slows down on this side, and then reverses itself. Okay, so what we're going to say here is that when v is 0, and at time 0, if x is starting at A. Well, if you think about this as a graph in terms of a wave, okay, if I do just a real brief graph, okay, where we're starting at A, if time is A, or at time 0, we're at A, and you make yourself a wave. Alright, so now that I've got this, sorry, I had a little issue with my microphone there, so if this seems really choppy for a second, it's because my mic died. Okay, if I draw a little graph here from A to negative A if I start at position A. So this is a position versus time graph. Okay, then we start at this spot, and this resembles a cosine wave. Therefore, in this particular equation, when starting at A, we'll have multiple equations for the position of the object. X could be a cosine of theta, which we talked about up there. X could be cosine of omega t, which I talked about up there. But I can make some substitutions as well. We could say that A is the cosine of 2 pi f times time, and I could also say that A is cosine 2 pi over the period times time. You could use any of those, okay? Something else to think about, okay, well, what about if it isn't this particular shape of graph? What if I make a graph where we start at time 0, we're at position 0? And you get a graph that looks more like this. Well, this looks like a sine wave. Okay, so if your position is 0 at time 0, as opposed to if your position is at A at time 0, then the function switches. Okay, so the position would be a sine of theta. And then, of course, we could repeat all of these with sine instead of cosine. Okay, so that's a little bit of an explanation as to some of the equations you're going to have in your packet, especially for IBers. Those are going to be huge. Okay. Now, the next thing that I want to talk about real quick is how position, velocity, and acceleration are all related to each other. Okay, so if you look at these graphs, I've got a graph of position versus time. Now, we should know at this point that the slope of position versus time is the velocity. So if I take the slope values of all my position versus time points, up here it's 0, here it's negative, here it's 0, here it's positive, here it's 0, here it's negative, here it's positive, and I draw the velocity graph, you're going to see that when the position is at its max, velocity is 0. When position is 0, velocity is at its max. When the position is at its max, velocity is 0. When position is 0, velocity is max. Okay, so they are off by a quarter of a wave, or in this case, they're off by a quarter period. Okay. If you take a look now and you talk about the velocity and the acceleration, okay, well, remember that the slope of a velocity versus time graph is an acceleration. Okay, so if I look here, negative, 0, positive, 0, negative, 0, positive, 0, and I graph that, okay, now I see that the acceleration is also out of phase, okay, from velocity, but you'll notice the real connection here is look at position and acceleration. Okay, when position is at its maximum positive position, acceleration's at its maximum negative value. When position is at its maximum negative position, acceleration's at its maximum positive value. Okay, so they're off by a half a period. They're exactly half a period off of each other. Okay, so that's how these things are related. Now that should also give you a little bit of an indication as to why, and we'll talk about this in a second, when one of the position equations is cosine, the other one is sine, or when this is sine, this is cosine, so on and so forth. They're always a little bit out of phase of each other. Okay. Now I've also got on here some other little helpful equations, and these are mostly for AP. I think these come in a little more handy for AP. But here's a couple general maximum velocity equations that could come about. We know that for any horizontal oscillator, you could get the maximum amount of energy when either you have the maximum kinetic energy, because right in that middle point, when the spring is not stretched at all, okay, then all the energy contained in it would be kinetic, or when it's not moving at all, meaning when it's stretched at the very end, it could be all elastic. So if these two things are equal to each other, if I set them equal to each other, the halves go away, I can bring the m over and then take the square root, and I could get an equation for the maximum velocity as the amplitude times the square root of k over m. Now, I could do another substitution with this to get rid of this k over m, if I think about the equation for the period of a spring oscillator, 2 pi square root of m over k, if I bring the 2 pi down, okay, I get t over 2 pi square root of mk, and then I invert both of them, then I've got square root of k over m, square root of k over m, so I know that 2 pi over t is the same thing as the square root of k over m. Therefore, you could write V max as 2 pi over t times a. You could also make the substitution to get rid of t and put in the inverse of t, which is the frequency, and write 2 pi frequency times a. Okay, so these are, I know there's a bunch of equations and a lot of things to get straight. I think it's going to get a little easier when we start doing some problems with it, but that's the start we've got. Okay.